Okay, we are now going to start the last kind of portion of our class. You noticed with the last exam you may have noticed that we skipped chapters 5 and 6. We went from chapter 4 to chapter 7. And now we're going to go back and look at chapters 5 and 6. Chapter 5 deals with the idea of sequences and series. And the very first section we're going to be doing in this video is going to be covering what a sequence is. And basically all a series is a sum of an infinite sequence of terms. So it may seem like the stuff in this chapter is completely unrelated to what we've looked at through calculus, whether it be differential calculus in Math 210 or moving on to integral calculus in this class. This stuff may seem kind of unrelated, but as we work through this chapter and into the next chapter, we're going to see how we can use a series, an infinite sum, to represent specific functions. And there's all kinds of applications we can do with this. In fact, if you ever get to differential equations, we can use infinite series and differential equations to model different types of physical behavior, from tiny electronic circuits to Earth orbiting satellites. There's all kinds of applications. So let's go ahead and jump into section 5.1. Again, this is called sequences. And this very first video, we're just going to get into the basics of what a sequence is. And then in the next video, we'll start to talk about how to find the limit of a sequence. So let's go ahead and look at this definition. Very simply put, a sequence is just an ordered list of numbers. So if we talk about an infinite sequence, and it's an ordered list of numbers, and notice the three dots at the end, it just keeps going and going and going. There's an infinite number of terms. And we always typically use n as what we call the index variable. So A1, A2, all the way to AN. Each of those things are called terms. So A1 is the first term, A2 is the second term, AN is the nth term of the sequence. And so a lot of times we will actually define sequences with a function or some sort of formula. And most of the time we can think of that as some function of n. Sometimes also we have recurrence relations or recursive sequences, and we'll talk about those towards the end of this section. But let's go ahead and look at an example to see how this works. So it says write out the first 5 terms for each of the following sequences. And so it says basically this right here, this n plus 1 over n squared, that's our formula that represents the sequence. And notice it says from n equals 1 to infinity, which is saying it's an infinite sequence. So if we want to write out the first 5 terms, what we can say is, well, let's go ahead and rewrite the sequence. We have n plus 1 over n squared. And of course, again, this goes from n equals 1 to infinity. Well, you just start with 1. So you start with 1. When you plug 1 in, you get 1 plus 1, which is 2, over 1 squared, which is 1. So we get 2, basically. 2 over 1, which is 2. Now we move on to 2. Move on to 2, you get 2 plus 1 is 3, over 2 squared is 4. And we can keep going. If you let n equal 2, you get, n equals 3, you get 3 plus 1 is 4, over 3 squared is 9. You need 2 more terms. Next one is going to be 5 over what? 4 squared is 16. And then we have 6 over 25. And this is an infinite sequence, so dot, 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 it keeps going. And let's just make a little note here. Again, this is the first term, so n equals 1. We have n equals 2, second term, third term, fourth term, fifth term. There's an infinite number of terms. All right, so that's kind of how it works. You'll also notice the pattern that in the formula, the numerator was n plus 1, and each of these, the numerator is increasing by 1. You have from 2 to 3 to 4 to 5 to 6, and then the denominators are all whatever n is squared. So these are all squares. Let's go ahead. I'm going to go ahead and let you do B on your own. So go ahead and pause the video and write out your those first 5 terms for part B. Okay, welcome back. You should have got the answer that you see here on the screen. A couple things to note about this one. Notice that this one did not start at n equals 1. Typically, the first term is what we're going to have when n equals 1, but in this case, the first term was n equals 0. The other thing you'll notice is that on the numerator, we have -1 raised to a power. Well, anytime you have a negative number raised to a power, it's going to alternate back and forth, positive, negative, between the terms, and we see that with the terms of this sequence. So let's go ahead and look at the note at the bottom of the page. It says, first, above we found terms by treating the formulas as functions and evaluating at integers. So that's pretty straightforward. We plugged in n equals 1, n equals 2, n equals 3 to evaluate and find the terms of the sequence. We could also go the opposite way, though. We could find a formula for the given sequence. So it could give us the list of terms, and then we could come up with the formula. So we'll get some practice doing that here in a little bit. The other thing is if it gives the term like this without specifically stating n equals 1 to infinity, we can just go ahead and assume that it starts at 1 and goes to infinity. That's what that notation means. All right, so example 2, this will be the last example in this video. It says to find a formula for the general term an of the sequence. The terms in the sequence are 1, -2/3, 4/9, and -8/27. So we want to come up with a formula. So I'm going to start out first just by rewriting this sequence. So we have 1, -2/3, 4/9, and -8/27. Notice first off that the terms of the sequence are alternating. So like we did in the last example, that means we're going to have a negative number raised to a power, and the first term is positive, okay? So also notice that the numerator seems to be powers of 2, right? 2 to the first power. So this is, let's make a little note here. This is 2 to the first power, 2 to the second power, 2 to the third power, and the denominator appears to be powers of what? Just like the numerator was powers of 2, the denominator is powers of, yeah, well, hopefully you said 3. So we can kind of go through this. And what I like to do is just kind of rewrite it as I was just saying. So I'm going to skip the first term here for a second, but the second term, we have negative, and we have 2 to the first over 3 to the first. And then the next term, we have positive 2 squared over 3 squared. And then we have again negative 2 to the third over 3 to the third. And then the first term was 1. Well, remember, if we kind of keep with this pattern of 2 to a power in the numerator, well, what's 2 to the previous one would have been 2 to the 0. What's 2 to the 0 power? Well, that's 1, and so is 3 to the 0 power is also 1. So we can think of that first one as being 2 to the 0 over 3 to the 0. And so that kind of gets us where we want to go. I did forget to rewrite this with the dots at the end. This is, again, an infinite sequence, so we need to indicate that it keeps going. So what's our formula here? So we know we have 2 on the bottom, powers of 2 on the top, 3 on the bottom, and we know it's alternating, so we need a negative number. So let's go negative 2/3. And we need to have the power be such that we get these terms that we were talking about. Now let's again note here, this is going to be the first term, the second term, third term, and the fourth term. And what you'll see from that is that looks like the powers, right? 2 to the first, 3 to the first. The powers are always 1 less than the index for the term index. So, because that was n equals 2, right? Powers of 1 for n equals 2. So what we can do is we can raise that to the n minus 1 power, because it's always going to be 1 less. And so you can double check to make sure that works, but it does in fact work. If you plug in n equals 1, this becomes the 0 power, which is going to turn that into 1. If you plug in n equals 2, the second term is going to be negative 2/3, and so on. So that's how we write out a formula for the general term of a sequence. In the next video, we're going to talk about finding the limit of a sequence, so I'll see you back in the next video. Thank you.